Okay, so before we talk about the Hilbert transform of a signal, first we talk about what is called analytical signal. So if you take a signal x of t, which is a real signal, okay, so if a signal x of t is real, then its Fourier transform will satisfy what is called conjugate symmetry property. Okay, so will satisfy what is called conjugate symmetry property. Okay, so its Fourier transform will satisfy conjugate symmetry property. So what does that mean? So the Fourier transform will look something like this. X of j omega will be equal to x star of minus j omega. So some people call it Hermitian symmetry also. So but both are same for us. Hermitian symmetry. So both are same. Hermitian symmetry or conjugate symmetry, both are same. So Hermite is a mathematician name. Okay, Hermite is a mathematician name. Okay. So if a signal x of t is real, then its Fourier transform will satisfy what is called conjugate symmetry property. So for example, because it satisfies conjugate symmetry property, so what do I do? First, let us assume that I take only positive frequency part of the Fourier transform. So how do we define that one? So let me denote it as x plus of j omega. So this is what? Positive frequency components. Okay, positive frequency component. So that is given by what? X of j omega when omega is greater than or equal to 0 else. Similarly, you can get the negative frequency components defined by x minus of j omega, so which will be equal to 0 when omega is less than 0, but x of j omega when 0 when omega is greater than 0, and x of j omega when omega is less than or equal to 0. So note that the signal x of t is real is very important. So if a signal x of t is real, then it will satisfy what is called Hermitian symmetry. So if we can get the positive frequency components and negative frequency components using these two definitions. So let us say this is 1 and let us say this is 2. So how is that 1 and 2 are related? So if x of t is real, they are related in this form. What is that? X plus of j omega will be equal to x minus of minus j omega whole conjugate. So the two components, positive frequencies and negative frequencies of the Fourier transform of a real signal, they are related like this. So let us see this with an example. So if you take x of t to be e power minus at, so for the e power minus at into u of t, so for this x of j omega will be 1 by a plus j omega. So here what is assumption? A is a real number and greater than 0. So here we assume that a is greater than 0. So for this signal, what will be x plus of j omega? So in compact form, so how do we get x plus of j omega is nothing but the Fourier transform for omega greater than or equal to 0. So that is same as we can write it as x of j omega into u of omega. So for the given signal, this will be equal to how much? 1 by a plus j omega multiplied with u of omega. Similarly, how do you get x minus of j omega? So that is nothing but x of j omega into u of minus omega. So if you multiply the original Fourier transform x of j omega with u of minus omega, you will get the corresponding negative frequencies of x of j omega. So this will be equal to 1 by a minus j omega into u of minus omega. So now I want to prove this property for this signal. Note that here x of t is real, which is satisfying this property. So for that, corresponding Fourier transform is 1 by a plus j omega. So if you look at this, what will I get? So let me take x minus of minus j omega. So that will be equal to 1 by a plus j omega into u of omega. So what will happen? X minus of minus j omega whole transpose will be equal to 1 by a minus j omega into u of omega. Sorry. So here x minus of j omega will be x of j omega and u of minus omega. This will be this. So x minus of minus j omega will be a minus of j omega, and the corresponding conjugation will give me this. But this is same as our positive frequency components x plus of j omega. So we have proved that for any real signal x of t. So we have taken an example and proved that for any signal x of t, this condition is satisfied. So from this discussion, what is that you have observed? We have observed that to get back the signal x of t, it is enough that you require only positive frequency components. Correct? So thus, what do we say? Thus, only positive frequency components of x of t are enough to reconstruct x of t. Okay, so from this discussion we have got this result. So next we proceed to the definition of analytical signal. So how do you define analytic signal? So a signal, so let us represent that it has x tilde of t is called analytical signal. Okay, so analytical signal of x of t if its continuous time Fourier transform is of the form, okay, if we can write that as x tilde of j omega is nothing but 2 into x of j omega into u of omega. Okay, so x tilde of t will be equal to, so what does it 2 into x of j omega into u of omega. So what does it mean? The analytical signal will have only positive frequency components of x of j omega. 2 is a scaling factor, so for convenience we have taken that. So this is equation 4. So now our task is to see the relation between x tilde of t and x tilde of j omega. How is that? X tilde of t and a Fourier transform, they are related. Okay, so if you look at this equation carefully, we can see this as multiplication of two signals or two Fourier transforms in frequency domains. Obviously, according to convolution theorem, what does it say? It will become convolution in time domain. Okay, so before we see that, so we have to we'll write on that. So we can see that 2x of t, so from this, okay, we see that 2x of t convolved with inverse Fourier transform of u of omega will have what as Fourier transform? 2x of j omega into u of omega as the Fourier transform. So what will be the inverse Fourier transform of u of t? We want to find the inverse Fourier transform of u of omega. So how do you find that? Again we have to use what is called duality property. So using duality property, so what do we get? Using duality property, okay, so using duality property, what do we get? U of t, we know that will have pi delta of omega plus 1 by j omega as the Fourier transform. So obviously pi delta of t plus 1 by jt will have 2 pi into u of minus omega as the Fourier transform. Again applying time reversal property, so what do we get? We'll get pi delta of minus t minus 1 by jt will have 2 pi into u of omega as the Fourier transform. Okay, but because Dirac delta is an even function, so what will I get? So this will become, this simplifies to pi delta of t plus j by t will have 2 pi into u of omega. So multiplying throughout with 1 by pi, we get delta of t plus j by pi t will have 2 into u of omega as the Fourier transform. So now again let us come back to equation 4. So what does it say? So let me call this fellow to be equation 5. So what happened? So we have got x tilde of t to be equal to, so x of t convolved with, see here 2 into u of omega will have what as inverse Fourier transform? Delta of t plus j by pi t. Okay, so if you take the convolution operation inside, this will be equal to x of t star delta of t, okay, x of t star delta of t plus j into x of t star 1 by pi t. Okay, so what happens? So this x tilde of t can be written as x of t plus j into xh of t. So why is that? So x of t star delta of t same as x of t, and let us see. So I have replaced the x of t convolved with 1 by pi t as xh of t. Okay. So what is that we have got? So we have got that xh of t, or x, we have got x tilde of t as x of t plus j into xh of t. So where we have defined xh of t as what? X of t convolved with 1 by pi t, and this we call it as Hilbert transform. Okay, so we call this fellow as Hilbert transform. So if you look at this equation, so let me call this as 6. So if you look at this equation, how do you get back your original signal x of t from its analytical signal? So this equation implies x of t is nothing but real part of the corresponding analytical signal. Similarly, the Hilbert transform of the signal will be equal to imaginary part of the corresponding analytical signal. So these two are very important results. So let us give some number to them. Okay. So if you have a signal x of t, how do you get its analytical signal? So you can see this as original signal x of t passed through some filter. Okay, so it is passed through some filter to get what is called analytical signal x tilde of t. So what will be the impulse response of this guy? X of t plus j by pi t. So that will be the impulse response of this filter. So if you pass a signal x of t through this filter, then you will get the corresponding analytical signal. Okay, so here we take a small example. So if you take x of t to be equal to cos omega naught t. Okay, if you take x of t to be cos omega naught t, I want to find the corresponding analytical signal. Okay, corresponding analytical signal. So how do you find analytical signal? Let us see the corresponding stuff in Fourier transform. So we have seen that x tilde of t will have what as Fourier transform? 2x of j omega into u of omega as the Fourier transform. So for our signal, for us, this example x of t is cos omega naught t. So obviously what will be x of j omega for us? X of j omega will be equal to pi delta of omega plus omega naught multiplied with delta of omega minus omega naught. Similarly, 2u of omega. So let us try to plot this x of j omega. So how does that look? It will look something like this. Okay, minus omega naught omega pi, and this is also pi. So this is our x of j omega. Similarly, how does 2u of omega look? So 2u of omega will look something like this. Okay, so this is 2u of omega. So if you multiply these two guys, how does that look? 2u of omega into x of j omega. So because this fellow is 0 beyond 0 towards negative side, so if you multiply these two, what do we get? You will get only positive Dirac delta, and the strength of that Dirac delta has become now 2 pi. Okay, so this is our 2x of j omega into u of omega. So we can write x tilde of j omega as 2 pi into delta of omega minus omega. Okay, so from this it is clear that x tilde of t, which is nothing but inverse Fourier transform of x tilde of j omega, will be equal to how much? E power j omega naught t. Thus, for a signal x of t equal to cos omega naught t, so what will be the analytical signal? E power j omega naught t. So let us write down that x tilde of t we got to be how much? E power j omega naught t. So if we expand this, what do we get? Cos omega naught t plus j sin omega naught t. Okay, so obviously we have seen that cos omega naught t is original signal, that is the real part of x tilde of t. So what will be x h of t for this signal? X h of t will be equal to imaginary part of x tilde of t, and that is nothing but sin omega naught t. Okay, sin omega naught t. So let us see one more example.